visualization to sort of give you some sort of an idea of the urgency of what we are trying to deal with. So what do we really mean by climate change? Why do we think climate is changing? The first predictions were based on physical and chemical understanding of the climate system, 150 years ago. And it came to, at that time, that scientists were thinking about the distance of sun from Earth and what the temperature of Earth would should have been. It was much cooler than the actual temperature of the Earth. John Tyndall in 1859 came up and found out that methane, water vapor, and CO2 are atmospheric gases that cause something called greenhouse gas effect, which is that when the solar radiation hits Earth's surface, it warms, and when it gets into an equilibrium and then tries to escape from the surface of the Earth, there are these gases which absorb that radiation. And if the concentration of these gases increases, then the temperature of Earth increases. And that's what we are experiencing. But it was Svante Arrhenius in 1896, which he said that if you change CO2 concentration levels, then the surface of temperature would increase through greenhouse gas effect. And he made some predictions which are a bit off, which is not too terrible, but these predictions are correct, and they're made hundreds of years ago. And actual numbers, because of the complexity of the system, may not be quite right, but the direction and the trends are. And if you want to read more about this and other evidence from observation,
Can we still hear you, Abha?
I think I have to change the audio. It's sort of in the wrong. You can hear me. Okay, all right. So I continue on. Sorry about that. Yeah, so we don't talk about 50% increase or decrease. We talk about something called equilibrium climate sensitivity. We talk a lot about, and that means that when you have increase of these greenhouse gases such as CO2, then there's more radiation being trapped within the Earth's atmosphere, and the response is that the global mean surface temperature rises. And when we reach an equilibrium state, then we have the equilibrium climate sensitivity of Earth, when you base that on some sort of observations, mainly based on paleoclimate data, because we have long proxy observations of temperature for that period, and then that can give you some sort of indication of what the equilibrium climate sensitivity of Earth is. But nowadays we use climate models to explore that space, and future climate, because future climate is something which we can't derive from the past, as correctly said by Kate in the previous presentation. So another thing which I think, I'm sorry, the plot is a bit small, but what we experience is actually local change. And that's why it's so difficult for people, ordinary people, to grasp that there is a global climate change, because what we experience is global, but the change is, we experience local, but the change is global. And if you look at the bottom line, the range and the x-axis, so the bottom line is only about 3 degrees in the global, which is on the right, and on the left you have the local, where it is 30 degrees temperature range. And if you had just changed by half a degree there, you would barely notice it in locally, but you would notice it quite dramatically in the global. And global temperature is, of course, much more steady, because some regions of globe are cooler, the others are warmer, and they sort of cancel each other most of the time. So the global climate is temperature is very steady. And so if there's a little change, then something dramatic is happening. The other thing which I'm glad I heard the last presentation, that we need to change our understanding of climate data and go over to climate knowledge. How do we transfer this data so that it is relevant for regional and local change, especially more information about extreme conditions are required. It's very hard to get from modeling, but if we are asked the right questions, then we could get some of this information, which is useful for optimal adaptation measures. Below that, there's a paragraph which I took out from the climate change report made for Auckland Regional Council by NIWA. And the only thing which I could find there was there's another report on extremes, but still the amount of information which is there is not yet there that you can really react to the events which are actually happening. So, and a little bit about this climate sensitivity, if I can find that. So what do we know about this equilibrium climate sensitivity? More work done in recent times from 1979 onwards, and we have a series of experiments, climate projections starting in 1996 to now. And there are several generations of models. The latest is the CMIP6, which came out recently. And we see that the assessed range of climate sensitivity hasn't changed much based on observations and models, but the model climate sensitivity is sort of having a wider range. Now we would ask, why is it so, and why does it not match? Although the models are improving, it's because we are adding more complexity to these models. We are taking away some of the things we just put in ad hoc in the models and replace them with actual physical and biological and chemical processes, which makes the model much more complex and give it much more range to explore. And that sometimes goes off what is reasonable and consistent. So people are working on it. If the range is too high, the medium range is okay, but some of the models are too warm. And then when we consider projections from those models, we have to be a bit careful and say they are too warm, and we should be careful. The other thing which we have to think about is the equilibrium climate sensitivity versus the transient climate response, which means that if you have CO2 coming into the atmosphere now, what is the temperature response right now? We don't have to wait hundreds of years to get to equilibrium response. And that's, if you look at the CMIP6, if you see the green bar there, that is sort of the transient climate response right now. But if you go and wait and do nothing, then you would reach the orange bar. So even if you're at 2 degrees now, you would reach 4 or 5 degrees in the future. And that is a cause for concern and deep concern. So the other thing which we look at is the global climate temperature versus observations and compare them with the model observations. Here, the black line on the left plots for the 3 generations of climate models is shown are the observations. The red line are the model mean of all the models which are from 1850 to present, or in different generations, of course, because they were earlier, the present was at a different earlier time. But if you look at all these runs, you see that the mean model temperature rise is very similar to the models. So it's not wrong, except if you look at individual models, these thin lines, they are quite, there's a lot of variability. And some of the worst models have dropped out in the recent times, but some more have been added with a very different range, but that they're running freely. We are not doing anything other than telling these models how much is the CO2 and all these greenhouse gases actually from observations, and they have to come up with their own climate. So, and the left, if you want to look at only observations and locally, we have the longest time series available from 1650 in central England. And if you look at New Zealand's 7-station time series, and that starts from something like 1900 onwards to present, then you can see that they both show that there's an increasing trend, a little bit less in New Zealand compared to the global average, but it is a cause for worry. Now, if I look at the 6 models which we did in a study for which we have a report on climate change projections, which is widely used by MFE and regional councils, we had chosen 6 models which behave very well for New Zealand conditions from a range of different models, and they're all different from each other. They're from different institutes to get the full variability. There are 2 things to note here. One is that the model temperature in the past, in the reference period of 2001 to 2050, is quite different for different models. Some models are very much cooler than the others, about a degree and a half difference. So if you say the reference temperature with reference to this its own past, of course, they all get to zero in the earlier period, but they then go out separate in the future. And other than for RCP 2.6, which is 2.5 watts per square meter of additional radiation due to anthropogenic addition of emissions, low emissions in this case, by 2100, you can see that eventually we are sort of reaching an equilibrium state. In this, you even remove CO2 from the atmosphere with means which we don't know yet, maybe trees, maybe not. But then the temperature steadies and we don't increase temperature or even decrease it a bit. So, and in the other models, we haven't reached equilibrium state. It continues to rise. That's a cause of concern. Now, if I go back and I've already talked about this. So why is climate change cause of concern? A few degrees here and there, not so bad. We would have to do forests and everything would have to adapt to it. But we are actually doing more than that. That 2 degrees change or 1 degree change means a lot in terms of circulation, in terms of more extreme conditions, more dangerous heat waves, and they can all come together, like we see that we could have droughts and floods in the same year. And yeah, there's something called social inertia. We're talking, politicians talking about global warming from the feeling of climate scientists sitting in my own room and doing all this research. And nothing seems to be happening until the reality takes over. This is a picture from Brussels, but you can take anywhere in the world and you would see these events happening. Now, of course, flooding happened always, but we are less prepared and it's happening more often and more severe than earlier. But there's a lot of papers around that which you can see. And even closer to home in New Zealand, Auckland, 2003, we had a conference in Auckland in that time, and my colleagues came from UK and were stuck in the airport on 27th of March, January this year. So it's happening here, and we have to take that very, very, very seriously. Yeah, so I talked a little bit about that equilibrium climate sensitivity and transient climate response. And as an example, I'm not sure if you can see this figure very well, but if you reach, for example, 2 degrees transient warming without intervention, that is removal of CO2, further warming would take place. If you stop today, it'll warm another 1.5 to 2 degrees over long time scales, maybe decadal to multi-decadal or even a few centuries later. But you would reach a very high temperature, which is unsustainable for life as we know it now. Another thing to worry about is this hysteresis. So that is, if you increase climate CO2 and other greenhouse gases to a level, say in this case, just to demonstrate, you go 3 times as much as earlier today, then the temperature, which is here, the CO2 increase or the greenhouse gas increase is in the black line, the red and the blue lines are the temperature and precipitation response, so they increase. And if you stop in 40 here, then the temperature goes down again and the precipitation goes down again, but to a new normal. So it's a new world that you will land, a new climate of that our world which you would land in. And it doesn't go back to normal anymore. So we don't know how much it will be. This is just a demonstration, but it could be just double as much as we have today, or even less than that. We don't know quite well where this instability arises that we can't go back. It seems that to the low emission scenario, which is very ambitious, which we nearly already passed because we haven't taken climate action, it may have been possible that we avoid the scenario, but we must avoid it at all costs. And another thing which we should be doing is better risk management and being proactive than with less need for recovery management and being more reactive. That means as an event like Cyclone Gabriel happens, we go over there and check what has happened. We have a response, recovery, and reconstruction. But better would have been we had mitigated, or we should still mitigate CO2 and take other mitigation strategies to do better planning. We have a prediction system and prepare for what anticipate these disasters and prepare for them so that there's less damage to society, to people, to their well-being, mental and physical. So, and now I come back to the New Zealand region. This is the region which is, you see New Zealand in the center, Australia, and around the large black solid line region is the domain where the weather influences us quite dramatically in that darker, bigger region with storm tracks and so on. And also the smaller region is then more contained weather. We look at these two regions to evaluate the weather or the climate models. And then we get something like that for New Zealand. We looked at these 6 models, which I talked about, low emission scenario to high emission scenario from RCP 2.6 to 8.5. And black is an historical period from, we did it from 1970, these runs from 1970 to 2005. And this is a surface temperature increase for the 6 models going to 2100, but a few models went further past. But you can see that other than RCP 2.6, all the models continue to increase at different pace. And the question was, how does the world look like at 2 degrees or 1.5 degrees? Now that would mean, now this is the relative change to the late 20th century. And the figures which I was showing earlier were the relative change to the early 20th century. So there's been climate change signal or imposed on this. So you have to shift the whole graph a little bit further to get the same numbers. But in this case, you can see that there's a dramatic difference between different models. And if you make a straight line horizontal through it, then the variability doesn't change. You still have a lot of variability. So it doesn't, if you take, you look at all the models in a certain period, or you go the other way, you don't reduce variability. It's a very complex variability. The other problem we have there is that if say you want to look at 1.5 degree climate change in all these emission scenarios, we reach them at different times. And in some models, you already reach that very early. This is a 20-year average starting at that date. And sometimes you reach it about 40 to 50 years later. So we know that the climate system is very complex and works at different scales. The atmosphere reacts very fast, ocean slower, and ice slower still. And if you give it 50 more years, then the whole system changes and it's distorted compared to the earlier system. So you would have even more variability in this case. But if you add them all together, you would get something, but it doesn't change and when I describe next what happens in New Zealand, the effect is the same, except that you would have maybe a little bit difference in numbers, but those numbers we have to sort of put them in context and sort of have some sort of understanding of, it's not the exact number, but roughly the range, because there's a lot of uncertainty around those numbers. So I'll talk a little bit about those numbers regionally, same as what Kate has shown. So for the temperature, we see that the highest changes are for summer and autumn and lowest for winter and spring. The trend doesn't abate in any season except in RCP 2.6 after 2100. Then the temperature trend goes down again, which I showed in a previous figure. If you have strong warming, strongest warming is over higher elevations and most prominent spring and summer, which is very bad news for our glaciers. We would lose almost all of them in a high emission scenario. And the daily temperature range increases with stronger trends in day than in nighttime, which means there's a different diurnal temperature range, which would affect, again, ecology. And then if you look at the extremes, the decrease in cold nights and increase in hot days, and percentage change is similar in different locations, but the number of frost days decrease would be the most where the regions are the coldest, and hot days would increase most in where the hot days are already quite large. So for precipitation, there will be reduction in the north and the east of North Island and an increase almost everywhere else, especially in the South Island's west coast. And in spring and winter season, getting wetter and the summers drier. Autumn is intermediate between these two. And the largest trends are on the west coast in the winter. All this information has been taken from the MFE's climate change report, which we did in which was prepared by NIWA in 2018, where I was involved. So the daily precipitation extremes, there would be more dry days throughout North Island and inland of South Island. The precipitation extremes, very wet and very extreme precipitation events would increase because they are directly connected to a physical theory that when the temperature is warmer, atmosphere can hold more moisture. And when it rains and when the conditions are right, and especially when there are extreme conditions, then it would rain much more because there's much more moisture available to precipitate as rainfall. In the wind, we see that because of mean sea level pressure is projected to increase over North Island in the east and south of the North Island in the summer season, which controls the whole circulation, we would have more northeasterly airflow and more anticyclonic high pressure conditions. And pressure would decrease south of New Zealand winter, resulting in stronger mean westerlies over central and southern New Zealand, which means that, which is consistent with the rainfall patterns there, which have more rainfall. Also, the extreme wind speeds would increase marginally, and this storms are likely to shift polewards, and so the storm tracks are likely to change. But there's very little. There's a huge uncertainty, and yeah, a lot more work needs to be done in this extreme space. So talking a little bit more about the climate extremes, this is an example from based on data from Panopai, Auckland observations. There's a long time series of these observations. And I looked at them for the past 22 years where the observations are quite good, and tried to compute the average recurrence intervals, how often at what level would a 100-year, 1 in a 100-year storm would look like, or 1 in a 1,000-year storm would look like. In observations, we see that the values are much, much higher than in the model past. That's the second row. And we need to do some sort of bias correction or adjustment to match the two. But what we also see is the 1,000-year event in the model past would become more or less something like a 100-year event in RCP 8.5 in mid-century. And in the end of the century, it would even bypass that. And I think this data outdated. I did this work a couple of years ago, and now we had these numbers would go upwards. I don't know what the latest numbers for NRPi are, but they are quite dramatic. And another dramatic picture is below there in the bottom here. This is from just the Met-Service webpage. And if you look at the month of January this year and the last year, this is the light blue and the dark blue colors, then we had 391.8 millimeters in January. And the year before that, we had 8.8. So we had a drought the year before. We had a huge wet and conditions which led to flood and other disasters. And the month later, it was still as bad, or not quite as bad, but quite bad. But it's dramatic. The variability we have to deal with is huge in orders of magnitude. Now talking about droughts, because yeah, droughts is of huge concern across the country, especially to the agriculture community, but also the environment is hugely stressed, as we saw in the last presentation. And the scale, the numbers are small because it's logarithmic. So it means small change means huge impact. So, and in RCP 8.5, most of North Island would be much, much drier than now. And also the South Island, large parts would be much drier. And but below that, I don't go much into droughts now because that's a separate presentation. I can talk a whole hour about droughts. And the bottom you see the rainfall range of models. So there's a lot of variability. The colors are the 4 RCPs, lower emission scenario to high emission scenario. And from left to right, you see north to south, some stations which we have picked up and looked at in the past and in the future, sort of. So it's mid-century and no, actually summer and winter, sorry. Summer and winter in the bottom. So then this is sort of the picture stays the same. There's some variation to that, but this is sort of, we would get now CMIP6 model results, which would give you some similar results. There might be small changes, but dramatically it's not going to change. So we don't get too much additional information when we do another a series of runs. So they have sort of stayed steady over the last few generations. So then we should think, are we asking the right questions to help people to adapt and to conserve and do other strategies? So things which I think we need to know is about extremes, of course, because that's what causes all these large impacts. And what is worrying is, for example, if you have the rainfall time series, which I showed you earlier for FENOP high, and you look at the end, if you take all the rainfall data for the past few hundred, all the data available, and you sort it, and you look at the end of the data set, you would have some extremes. And if they don't get more and more rare quickly enough, then the decline is slower than exponential. That means there are many more rare events which are not that rare anymore. And that's what is happening. So example for that is that we had Bola and Gabriel is more extreme than the earlier event. And that is not normal for if you would have a normal distribution of these events. So and concern is also that these tails might get even fatter when they of this distribution, that they don't fall very quickly, and the extremes just occur very rarely, even more rarely. They occur more frequently, and that's then climate change would make that they're already more frequent now, partly due to climate change, but future is even worse. And this also means that the historic data is only a poor guide for our prediction. So we need to do much more work in this space to figure out what the distribution of extremes are, what if situation, that when we need to know what conditions do we need that the event becomes so severe. So there has to be a lot coming together for that. For example, for Cyclone Gabriel, there was marine heat waves, the soils were saturated, it had been extremely wet. Then you had the Enzo state in La Nina, which brings the winds in the right direction. And that event, that cyclone, persisted over the region for a long period of time, which continued to rain in the same place. And then you go over to compound events like heat waves, droughts, and fires, which we'll talk about later. It's quite important to do that. And this goes into all, we have to convert this data to fit for purpose knowledge. And my last slide is that the take-home message that mitigation is critical. If we don't do mitigation, if we don't reduce our CO2 levels, we will reach in a regime from which there's no going back. We have to avoid that at all costs. We should rather become proactive than reactive, right? Ask the right questions and translate climate data into information and knowledge, which helps in adaptation. And we need to act fast in pace with the gravity of the crisis that we are facing. Okay, and there should be no misplaced optimism. We will not be all right, as people in Hawke's Bay have experienced. So we have to, and Auckland. So we have to really take action and not, which must be effective and not just accounting tricks. Thank you so much for listening to me and giving me this opportunity to talk here. I'm sorry, I can't hear